Hello, this is the Clean Ballast Water team. My name is Ariana Redondo.
I'm Martha Priestley.
And I'm Alex Williams.
Our client was Andy Praise from Integrity Pools located in Florida. Our faculty advisor was Dr. Lacey, and our project manager was Dr. Nicholas.
Our project involved the disinfection of water in ballast tanks. Ballast tanks are used in ships for buoyancy and stabilization purposes. When these ships arrive into ports around the world, they have to discharge this water that's stored in these tanks. When this happens, this spreads invasive species and other disease. Our client's system will use ozone and sodium chloride to disinfect this water while it's stored in the ship's ballast tanks. These chemicals were chosen for their bactericidal, algicidal, fungicidal, and clarifying properties. If you look on the image on the left, this is how the system will look once it's finally implemented. The system we actually did testing on is on the right. You can see the tank. Water will flow from the tank through the pump, from the pump to the top of the ozone column. It will leave the ozone column, will flow back into the tank, and this will be repeated. Next slide. Okay, this is our client's actual patent. It was an ozone dissolution chamber. If you look at number 42 at the top left image, that is the ozone injector. The ozone will be injected through a Venturi injector. They will be forced into the top of the column. In the top of the column, the large bubbles will tend to gravitate and stay there, and the smaller bubbles will be broken down by the impact of the water. The finer the bubbles, the lower the buoyancy of these bubbles, and therefore the greater the likelihood that they will be entrained in the downward and outward flowing water. So ultimately what's leaving the tank is a super fine bubble, or in some cases completely dissolved ozone. Our client's technology in theory is more efficient than other ozone injectors due to the laminar stratification of these gas bubbles, meaning that the larger bubbles will remain on the top of the tank until they're broken down, and only the smaller bubbles will be leaving the column. This smaller bubbles means better contact with particles in the water, which means better disinfection in the system. As the flow is recycled through the system, the ozone concentration will continue to increase its oxidative potential and will increase the efficiency of the entire system.
We had three design objectives. We had to decide how to collect samples of the ballast water, what treatment methods we were going to use to treat the water, and then how to test those treatment methods that we used were actually working. Our project deliverables were that we had to produce data on how viable each treatment method was. This is to show how well each treatment disinfected.
For constraints, our biggest constraint was time, due to the fact that our second semester, when we were going to conduct all of our testing, was basically cut in half. We had to work with what we had, and yeah, sample availability was also a big issue because we wanted to make our sample relayed and resemble the real world as much as possible. So we were planning on getting it from Trinity Bay, but since that got canceled, our client was able to get the sample and drive it down to College Station, so our sample availability was reduced. For budget, our client didn't really give us a limit, but since everything was going to come out of his pocket, we wanted to make it as economic as possible for him. So yeah. For the design approach, we asked ourselves these 5 questions. We asked, how were we going to obtain the samples to test? What organisms we would test for in the water? How we were going to test for these organisms? What was going to be the most cost-effective way to test the effectiveness of our client's technology? And finally, given our time and budget constraints, which design option would work best?
So we came up with 3 sample alternatives and 3 testing alternatives. The first sampling alternative would be to create our own ballast water. This would have involved matching the salinity and other elements found in ocean water. This would have been pretty difficult. Many of the elements found in ocean water, such as bromine or boron, react with the water and create other oxidative chemicals. And without these in the water, the experimental data would not have been representative of actual accurate data. Sample acquisition number 2 was to collect samples from ships' ballast tanks that were coming into the port of Houston. This would have been the best option. It would have been the most representative of a real world scenario, but there was many problems such as permit acquisition to be able to even get onto the ports, much less ask the ships to collect their ballast water. So we decided on alternative number 3, which was to collect samples from the ocean in simulate conditions alike to those in ballast tanks. This will be discussed in the next slide. We also came up with 3 testing options. The first was various experiments to determine if samples would pass minimum discharge content requirements. This would have involved buying a plankton net, which would have filtered out organisms smaller than 50 micrometers and collected organisms larger than 50 micrometers. These would then be counted and we would have to make sure that value was lower than the max discharge limit of organisms allowed in the water. This would have been a pretty difficult option given the time constraints of the project. The second option was a BW700 ballast water validation kit. This had many devices on it. It was a very expensive device, and not all the devices would have been applicable to the testing. So this was discarded. But this would have been very useful if we were actually on a ballast tank trying to make sure our water met requirements. The third option was to test for ATP. This is what we decided to go forward with, and this will be discussed in the next slide.
So for our final design solutions, we start with the sampling solution. Our client collected water at Trinity Bay for salinity, and then we seeded 2 out of the 4 35-gallon samples with organisms. The chosen organisms represented living things commonly found in ocean water, and testing these organisms showed the range of disinfection ability of the testing system. For treatment solutions, we used were ozone and ozone plus sodium chloride. These treatment solutions were used because this is what the client presented us with. And finally, our testing solution, we conducted ATP testing before and after to determine percent disinfection of the water treatment.
For the organisms we were gonna seed, the total cost was $130, and the ATP testing kit that we decided to use was $2,500, and the grand total was $2,630.
So while it's clear that there is disinfection in all of the testing that we did, the amount of total suspended solids in the sample water was too high. This was due to the amount of silt, sand, and heavy debris that was taken, like Alex had said, in low tides from Trinity Bay. The samples had a large oxidation reduction potential demand that had to be overcome by the ozone. And since this ORP value of 650 millivolts was not reached, it is likely some chlorine was created in the system. Chlorine is a carcinogen that's prohibited for discharge from the IMO. And then due to difficulties and roadblocks from the COVID-19 pandemic, further acquisition and testing was not possible.
As Martha mentioned, the testing was basically successful. We saw disinfection. But the amount of TSS in the original sample that was collected was too high. So to improve the efficiency of the project and of the system, we would recommend either when you collect the samples to have a sample that has a lower total suspended solids. When you collect ballast water from the ocean, it will not have this high of a total suspended solid. It was just because it was taken during a low tide and collected a lot of the debris that was on the bottom of the water. The second recommendation would be to use a filter if the TSS is too high in the system and it is found that this cannot be overcome through multiple tests, we would recommend adding a filter to try and reduce some of the solids in the system before and allow the ozone to better perform more efficiently. The last option to increase the efficiency would simply be to inject more ozone into the system, increase the ozone injection rate to overcome the ORP requirement.
We'd like to thank our client, Andy Press, for letting us work on this project, and his client associates, Brian Press and Bill, our faculty advisor, Dr. Basie, and our project manager, Dr. Nikolov. Thank you.